So criteria for injectivity. And feel free to shout out or, because again, it's kind of, you guys have really good poker faces. Okay, so recall that Q is an injective R module if and only if. Okay, so we have that mod R, and then so what was it? So it's that if I take injections, they're going to surjections. Okay, so we need to check that injections go to surjections. Okay, and so we can write a similar diagrammatic condition out. So we get a similar diagram or formulation of this condition. So this is similar to the one that we had for projective modules. Okay, so if you have a map here, so what does it mean? So so given that this is an injection, so if V prime to V here, so if this is an injection, let's call this F. Okay, so let's suppose that this is an injection. This is an injection. Right, so this tells us that, okay, so now we're just going to apply Q to this, or the functor co-represented by Q. So now it flips everything, right? So then we have VQ. This is the pullback map here, and this is mod R V prime Q, like so. Okay, so what it's saying is that every map, so what does this map to? So this takes a map here, phi, and it maps it to F star of phi, which is phi composed with F. Okay, so the other one was just like a direct, you just directly compose. This is backwards. Okay, and so let's look at what this means. So let's just write this. So we have a map from, so we have V prime to V, right? And then we were given a map phi to Q here, Q, right? So this is what we were given. And so what we get is we get the pullback thing. So this is F. Right, and so what we get is we get this thing. And so we get this map here, F star phi, which is the composition of the two. Okay, so this is just the regular map. Okay, so this is what I just drew here is, so I just drew this thing in terms of diagrams. So this is the same drawing. Okay, so this is the same. Okay, the surjectivity part, right? So this surjectivity part here, the surjectivity part, okay, it says that, and in this, for this part here, for the what's in the purple circle, oh. Okay, so what's in the purple circle here, this doesn't need, you don't need an injection for this. This is just a thing that exists totally generally. Okay, this is just functorial. Okay, for the surjectivity part, you do need that this be an injection, but it's saying that, okay, so for the surjectivity part, it says that here, let me go back to making this a little bit bigger. It says that when you have a situation like this, okay, so this is an injection and you have a map here, like this, psi, right? So if you're given this, then by Q being injective, okay, it's saying that this thing is a pullback. So whenever you have this inclusion like this, and you have this map like this, Q, there's a map here such that this thing is equal to the pullback like this. Okay, so this is another criteria for so this is what you get. This is what you get from Q being injective. It says that this thing exists, right? That there exists a map down to Q such that psi is the pullback. Okay, and so that's another way of formulating injectivity, and this is the exact same. So it looks like the same thing that we did with projective. Okay, it looks very similar. I don't know if the arrows are exactly reversed, but yeah, you can look at it, and this is kind of a dual condition. Okay, so the point is that the upshot is that here this condition is useful for checking when things are injective, when modules are injective. And it's equivalent to what we just said before about having so injective maps go to surjections under the thing that's co-represented by the module. Okay, so this is just another way of writing out the same thing, but maybe this is, you prefer to think about it this way. Okay, or it'll be useful to think about it this way. Okay, so so to give examples of injectivity, there's kind of a useful criteria. Let me just write this down. So to give examples of injective modules, it is we can use a criteria. Okay, so so let me write this down. So this is called this is a theorem. It's called Baer's criteria. Okay, and it says that so what we'll do is we'll let M be an R module, or let's say yeah, so let M be an R module. Right, then or okay, so let's actually do it like this. Let's let Q do this way. So it's going to be injective module. So let Q be an R module. So Q is an injective if and only if for every inclusion of ideals. So it says that like it suffices to test on ideals of ideals I in R. So this is an injective morphism of R modules. The map here mod R. So this is, so we have a surjection here. So we have here to Q mod R I to Q is surjective. Okay, so this is saying that that every, okay, so what is this saying? So the idea here is I guess the upshot here. So you can test injectivity on the stupidest modules that you can possibly think of, right? Injective maps of R modules. So you can test injectivity on inclusions or inclusions of ideals. Injectivity of a module. On inclusions of ideals into their rings. Okay, so it gives us a nice way of determining when, you know, Q is injective. So normally, right, let me just emphasize this, right? So what this is saying in terms of this diagram here, right, is that you could just test this. You don't have to test every V prime into V. You only need to test I into R. Okay, so it's saying that in this diagram, so you only need to check. So if you have I into R, like this, and then how did we write this? So if we have this thing, Q, right, then that there exists some map like this, right? So normally we would have to do, you would think that you'd have to check every inclusion injective map of R modules, but you only need to check it on ideals. Okay, and as a corollary of this, is that divisible maps. So divisible, so okay, so let R be a PID. Let me give you a definition. And then I'm going to give you an exercise. Okay, so let R be a domain. So a group, in our module, M is divisible if and only if for all M in M and all R in R, there exists some M prime such that MR, let's see how we do this, M R M prime is equal to M. So so this is what we have. Okay, so what this is, how do we look at this? So this is saying that, like, so the way to think about this, you think about this as M divided by R is M prime. Right. So like there's something that it's, you know, there's something that divides M, right? So you can kind of divide by elements of R. Okay, so a theorem here. So maybe this is a corollary of the Baer criteria. And this is maybe a good, well, maybe I should say that this is an exercise. Let's do this as an exercise. So this is a good one. Okay. If R is a PID and Q is divisible, then Q is injective. Right, and I think this is an if and only if, but I don't know off the top of my head, and I don't have it written down. But this is in dumb and foot. But yeah, so this is if R is a PID and Q is divisible, then Q is injective. So what are the examples? So now we can write down a bunch of examples. Like, so Q mod Z, Q as a Z module, as a Z module is divisible. Q mod Z as a Z module so the fraction field in general, you know, frac R, as an additive group, as an R module for R PID works, is a divisible R module. Okay, so yeah, here are your basic examples. Okay, and that's all I want to say about that. Okay. All right. Okay. So so let me move on to tensor products, and unless you guys have some questions. I think you guys should start working with this stuff, and then you'll see that this is. I claim that this is not so bad.
What's a?
And I'm not going to prove this one here. So this one, the proof is in dumb and input. So I'm just going to omit this proof.
What's a flat module? When you start this,
that's my next. Okay, there you go. That's what's next. Okay, good, great, excellent question. Okay, so flatness